So now we're going to talk about differentiability. And again, we're going to reference what happened back when we had a function of just a single variable. So we'll start with a recall fact. If your function y equals f of x is differentiable, then the differential, which was dy, which was f prime of x dx, can be used as an approximation for the value of delta y, which is f of x plus delta x minus f of x. So one of the important things about differentials is that you can use them to approximate your function, but only if it's differentiable. So we're going to need to know what differentiable means here for a function of more than one variable. So we're going to say a function f that's given by z equals f of xy is differentiable at a point, at some point x naught, y naught, if delta z can be written in the form, we can write delta z as the partial derivative of f at x naught, y naught, delta x, plus fy, the partial derivative at y at x naught, y naught, delta y, plus epsilon 1 delta x plus epsilon 2 delta y, where both epsilon 1 and epsilon 2, they're going to go to 0 as xy, delta x, delta y go to 0, 0. So you have to be able to write delta z in this kind of format here. So let's look at an example. I want us to show that the function f of xy will be x squared plus 3y is differentiable at every point in the plane. So we're going to start with delta z. The formula for delta z is that it's f of x plus delta x, y plus delta y, minus f of xy. So this is, plug these into your function up here. So you would get x plus delta x squared plus 3y plus delta y minus the function, which is x squared plus 3y. And now you're going to have to FOIL and distribute. In those first two terms, you'll get x squared plus 2x delta x plus delta x squared plus 3y plus 3 delta y minus x squared minus 3y. And you should see some terms that cancel, this x squared and negative x squared, negative 3y and positive 3y. So in the end, this is 2x delta x plus 3 delta y plus delta x squared. So I'm going to go back up to my function, and I need to look at my function and find the partial derivative. So what would the partial derivative with respect to x be? It would be 2x, and the partial derivative with respect to y would be 3. So here, 2x, that's my partial derivative with respect to x. So this would be fx xy delta x, and then 3, that's the partial derivative fy delta y. And then I'm going to expand out this delta x squared as delta x times delta x. And then I also am going to write plus 0 delta y. There's no delta y term. And if you compare what we have here in this line with the formula and the definition, you'll see that epsilon 1 would be delta x, and epsilon 2 would be 0. Okay, so here's my delta y, delta x, delta y. Here's my epsilon 1, here's my epsilon 2. And these are both going to go to 0 as delta x, delta y goes to 0, 0. So we meet the conditions of being differentiable, and I can say f is differentiable at every point in the plane. Now I do want to give you some theorems that will help us determine if a function is differentiable. So the first one is theorem 13.4 from your book, and it says if f is a function of x and y, where fx and fy are continuous in an open region R, then f is differentiable on R. So one way of seeing maybe that your function is differentiable is to look at your partial derivatives here and here. And as long as your partial derivatives are continuous, you know that your function is going to be differentiable. And then I want to give you one more. This is theorem 13.5. which says if a function of x and y is differentiable at a point, then it is continuous. At that point. So this is something you also saw back with a function of a single variable, but it's also true here for a function of two variables.